Welcome to Optical Effects of the Atmosphere. The atmosphere does more than just produce our daily weather. From sunny to cloudy days, dry or wet, stormy or snowy, the atmosphere is also capable of producing colorful displays when conditions are right. Some of these optical effects include rainbows, halos, sun pillars, and sundogs. To better understand how the atmosphere produces these bursts of color, we need to understand a little something about light. Light is electromagnetic radiation with a wavelength that is visible to the eye. This is the light we see. Visible light is actually composed of all the colors of the rainbow. We can see these colors by using a prism. The properties of a prism allow it to break visible light apart into its component colors, colors ranging from the darkest reds to the deepest violets and everything in between. In the atmosphere, under certain conditions, water drops and ice crystals can act as a prism, allowing us to see the various colors that make up visible light. It's because of these properties that we get rainbows and other atmospheric optical effects. Let's look first at rainbows. It's safe to say that all of us have seen a rainbow. For a rainbow to develop, we need to have rain falling in one part of the sky with sunshine in the other. To see the rainbow, though, you will need to have the sun at your back and face the direction where the rain is falling. So just how are the rainbow's colors produced? As mentioned, raindrops can act as a prism. As sunlight enters a raindrop, part of the light passes through it, but another part is broken into visible light's component colors, such as red and violet. The light is refracted inside the drop, with the colors exiting at angles from 40 to 42 degrees in reference to where the sunlight enters the drop. However, if the water drops break visible light into all the colors, why don't we see colored light all across the sky? This has to do with the angles at which the light exits the water drops. Let's look at this more closely. As sunlight enters the raindrops, part of the visible light is refracted, and colored light exit the drops back toward our eyes. However, these colors are seen at specific angles between 40 and 42 degrees, with each color seen at a specific angle. Because of this, each drop produces only one color we can see. Instead of seeing random colors everywhere, we get the distinct shape and color of a rainbow. Along with this, because each person views the rainbow slightly different than another person, such as with differences in height and where they are standing, different drops will produce the different colors. As a result, the rainbow you see is actually a different rainbow than someone right next to you will see. The rainbow is distinctively your own. In this image of a rainbow, it's rather easy to see the bow in the center of the picture. However, if you look closely to the right of the main primary bow, you can see a faded secondary bow. This secondary bow develops as a result of light entering raindrops at angles that allow the light to make two internal reflections in each drop. Each reflection weakens the intensity, making it faded in appearance. The colors are also in reverse, with red on the inside and violet on the outside. So we have seen how the combination of water drops and sunlight can produce a rainbow. Now let's look at how sunlight can interact with ice crystals to produce optical effects such as halos, sundogs, and sun pillars. Let's start with halos. If you look closely at this image of the sun, you can see a circle of light surrounding the sun. This ring of light is called a halo. Halos develop in response to light refracting off ice crystals suspended in the air, usually from high, thin clouds known as cirrus clouds. Halos are usually a bright white ring, but can also have color. Halos can also form around the moon. In this image, just off center, off the middle, you can see a colored spot of light. This is called a sundog. Sundogs also develop due to the refraction of light through ice crystals and can be found with halos at times. They are approximately 22 degrees left, right, or both from the sun. Sundogs are also known as mock suns or perihelia, which means with the sun. In these images, you can see beams of light seemingly coming out of the top of the sun. These shafts are called sun pillars and develop as sunlight reflects off ice crystals slowly falling through the air. Sun pillars will be seen when the sun is low in the sky, at sunrise or sunset, and when cirrus clouds are present. Now let's look at some other common questions related to the sky and its various colors. For instance, why are clouds white? The sight of white clouds, whether they be high and wispy, low and puffy, or tall and powerful in the case of storm clouds, is something we see on an almost daily basis. But why are they white? As visible light enters the cloud, most of the light is scattered by the cloud drops that make up the cloud. When all visible light is scattered, the resulting light is white, so therefore clouds usually appear as white. However, many times, as in the case of rain clouds, clouds will appear gray to black. Why is this? There are two basic reasons. One is as a cloud grows more dense, it absorbs most of the visible light. When all visible light is absorbed, the resulting color is black. Second, as the size of the cloud drops increase, they also absorb more light, leading to a darker appearance. Bottom line, the denser a cloud is and the more water in the cloud, the darker it will be. Now that we have addressed the color of clouds, let's look at the color of the sky. Why is it blue? The color of the sky depends on the interaction of air molecules with the sunlight. In this image, the blue circles represent air molecules. As sunlight hits these molecules, the shorter wavelengths of visible light are scattered toward our eyes, namely violets, blues, and greens. However, if this is the case, why don't we have green or purple skies? This answer lies with how our eyes work. Our eyes are more sensitive to blue light as opposed to green or violet. Therefore, the combination of these scattered pieces of visible light appear to us as blue. However, at sunrise and sunset, the sky can become a brilliant red or orange. How does this happen? Let's look at our air molecules again. At sunrise and sunset, the sun's rays have to travel through a lot more of the atmosphere to get to our eyes, thus interacting with a lot more air molecules. Because of this, by the time the light reaches our eyes, all the shorter wavelengths of light have been scattered away from our eyes, leaving longer wavelengths of yellows, oranges, and reds. Now let's look at the optical effect known as the Aurora Borealis, more commonly known as the Northern Lights. The aurora is a visual light show of generally greenish whites and reds originating from the magnetic North Pole high up in the atmosphere due to the interaction of particles from the sun colliding with air molecules. There is also an aurora australis associated with the South Pole. Let's examine how auroras are created. First, the Earth is surrounded by a magnetic field which originates from both magnetic poles. From the sun, a steady stream of charged particles are sent out, which is called the solar wind. Generally, the magnetic field of the Earth deflects the solar wind away from the planet, but at times, some of these particles will be caught in the magnetic field near the poles and brought downward into the Earth's atmosphere. The atmosphere is composed primarily of nitrogen and oxygen molecules, which in this diagram are represented by the circles on the right. As the charged solar particles move downward through the atmosphere, they start to collide with oxygen around 250 miles above the Earth's surface. This collision causes a release of energy in the form of light, and in this case, red light. As the particles get lower, oxygen releases a greenish-white color. As the particles continue downward, they interact with more nitrogen, which results in a red color. The most common aurora color is a greenish-white, resulting from the collisions with oxygen roughly between 180 and 60 miles above the Earth's surface. Some other notes of interest about the Aurora Borealis. The intensity of an aurora depends on how active the solar cycle is. The stronger the sunspot activity, the stronger the aurora. The Aurora Borealis is generally centered near the Arctic Circle, which in North America runs from northern Alaska through northern Canada. The best times to view an aurora is from late evening through the early morning hours, with peaks in the spring and fall. The average aurora extends as far down into the atmosphere as 60 miles, with the upward extending averaging from 120 to 200 miles. Auroras have been known to disrupt radio communications, radio navigation, some defense-related systems, and power transmission lines. On average, an aurora extends as far south as the Canadian-U.S. border 2 to 4 times a year. It can reach Mexico 1 to 2 times a decade, and even the equator once in 200 years. So what have we learned? Visible light is composed of all colors, and we can use a prism to break light into these colors. Water drops and ice crystals in the air can act like a prism, and it's because of this that we get optical effects such as rainbows and halos. Rainbows are caused by light refracting off the inside of water droplets. In order to see a rainbow, you must be facing the falling rain with the sun at your back. Halos, sundogs, and sun pillars develop as a result of light interacting with ice crystals. The ice crystals are generally from high, thin clouds called cirrus clouds. The color of clouds depends on the density of the cloud and how large the cloud droplets are. Most clouds are white because the cloud drops scatter visible light. When all visible light is scattered, the resulting color is white. As a cloud becomes more dense or the cloud drops increase in size, the light cannot penetrate the cloud and is absorbed. When visible light is absorbed, the resulting color is black. The sky is blue because air molecules scatter the shorter wavelengths of visible light toward our eyes, violets, blues, and greens. The sky does not appear purple or green because our eyes are more receptive to blue. Sunrise and sunsets are more orange to red in color because the sunlight has more of the atmosphere to travel through. This results in the violets, blues, and greens being scattered away from our eyes, leaving yellows, oranges, and reds. The Aurora Borealis, more commonly known as the Northern Lights, results from the collision of solar particles ejected from the sun with molecules in the upper parts of the Earth's atmosphere. Oxygen and nitrogen are responsible for the greenish-white to red colors that are most commonly seen in auroras. For further information on any of the topics we have discussed, here's a listing of some good resources.